Inside every proton, there is a force so strong that it shapes nearly all the mass of the visible universe. And yet, no experiment has ever seen its messenger exist on its own. The gluon is real, essential, and unavoidable, and still, it never appears by itself. That is not a limitation of our instruments. It is a rule written into nature. This story begins at the smallest scale we can probe, where quarks are bound together by interactions described by quantum chromodynamics, or QCD. Gluons carry this force, but unlike light or gravity, they refuse isolation. They act everywhere inside matter, while leaving no solitary trace behind. What seems invisible is doing most of the work. In this episode, we follow the evidence carefully, step by step, into the structure of matter itself, where mass, force, and confinement are inseparable. We begin with part 1. Why can't we ever see a gluon alone, even though it's real? The most unsettling fact about gluons is not how difficult they are to detect, but that the laws of physics themselves appear to prevent them from ever existing alone. Every particle detector ever built, every accelerator ever switched on, and every high-energy collision ever recorded has pointed to the same outcome. Quarks appear only in bound groups, and gluons appear only through their influence, never as isolated objects. This pattern is not a technological limitation. It reflects how nature is organized at its most fundamental level. In theory, gluons are straightforward to define. They are the carriers of the strong force, the interaction that binds quarks together inside protons and neutrons. Without this force, atomic nuclei would not survive, stars could not sustain fusion, and the matter around us would not remain stable. Quantum chromodynamics, known as QCD, describes this interaction with remarkable accuracy. Within that framework, gluons are as essential as electrons or photons. Yet their behavior is profoundly different. Photons move freely through space. Electrons can be isolated, stored, and counted. Gluons cannot. No matter how extreme the conditions, no experiment has ever produced a free gluon. The first hints of this behavior appeared in the late 1960s, when physicists at the Stanford Linear Accelerator Center began probing protons with high-energy electron beams. These deep inelastic scattering experiments revealed that protons were not smooth, indivisible objects. Instead, electrons scattered as if they were striking point-like constituents inside the proton. Richard Feynman famously referred to these constituents as partons. At first glance, the data suggested that quarks might behave as nearly free particles when probed at very short distances. But attempts to extract those constituents told a different story. When researchers tried to separate quarks from protons, they never appeared on their own. Instead, new particles formed. The act of pulling did not release building blocks. It generated additional bound states, as if the energy used to separate quarks reorganized itself into new matter. The same pattern emerged when physicists searched for gluons directly. In 1979, experiments at the Petra electron-positron collider in Germany produced a decisive result. Certain collisions produced 3 distinct jets of particles instead of 2. 2 jets matched what was expected from a quark and an antiquark moving apart. The third carried momentum and energy that could only be explained by the emission of a gluon. This was recognized as the first clear experimental evidence for gluons. Yet, even in this landmark discovery, the gluon never appeared as an object that could be isolated or tracked. It showed itself only indirectly, through a cascade of hadrons produced as the strong force reorganized the energy of the collision. The gluon left a clear signature, then disappeared into confinement. The reason for this behavior becomes clearer when the strong force is compared with electromagnetism. Electric charges interact by exchanging photons, and that interaction weakens as distance increases. The field spreads out, allowing charged particles to separate. The strong force behaves in the opposite way. As quarks are pulled apart, the interaction between them grows stronger. Instead of fading, the energy stored in the gluon field increases roughly in proportion to the separation distance. Both experimental evidence and lattice QCD calculations support this picture. Rather than spreading through space, the gluon field tightens into a narrow region often described as a flux tube. Pulling harder does not weaken the connection. It concentrates energy. Large-scale numerical simulations, developed since the 1970s and refined using modern supercomputers, show what happens next. As separation continues, the energy stored in the gluon field becomes large enough to create a new quark-antiquark pair from the vacuum. The original system does not break apart. It splits into two bound systems. Isolation never occurs. This phenomenon is known as confinement, and it applies not only to quarks but also to gluons themselves. The underlying reason lies in a defining property of QCD. Gluons carry the very charge they transmit. In electromagnetism, photons are electrically neutral and do not interact directly with one another. In QCD, gluons carry color charge, which means they interact with other gluons. The force is not a simple exchange between particles. It is a network of interactions that reinforce themselves. This self-interaction transforms the strong force into a non-abelian gauge theory. Within this structure, the equations allow force carriers to bind, curve, and concentrate. The gluon field does not disperse smoothly. It organizes itself into confined configurations. From the standpoint of the theory, a free gluon is not just difficult to produce. It is not a stable physical state. Decades of experimental searches reinforce this conclusion. During the 1970s and 80s, physicists looked extensively for evidence of free color charge in cosmic rays, lunar samples, and accelerator debris. If quarks or gluons could exist independently, traces of fractional charge or unusual interactions should have appeared. None did. The absence was consistent across experiments and environments. Today, confinement is treated as an empirical fact, even though a complete analytic proof from first principles remains an open challenge. The Clay Mathematics Institute's prize for proving confinement and the existence of a mass gap reflects this situation. Physicists observe confinement constantly. What remains unresolved is the formal mathematical demonstration that makes it inevitable. Extreme conditions provide further insight. In heavy ion collisions at facilities such as the relativistic heavy ion collider and the Large Hadron Collider, nuclei collide at energies high enough to form quark-gluon plasma. In this state, quarks and gluons move more freely over short distances, resembling conditions in the early universe. Detectors observe collective behavior consistent with partial deconfinement. Yet as the plasma cools, confinement returns. Gluons do not persist independently. They reorganize into hadrons once again. The same physics shapes the universe on much larger scales. Measurements of proton structure show that most of a proton's mass does not come from the intrinsic masses of quarks. Instead, it arises from the energy stored in gluon fields and the motion of confined quarks. More than 90% of the mass of ordinary matter originates from this confined dynamics. Gluons determine the weight of the visible universe while remaining permanently bound. As David Gross once summarized, the remarkable feature of QCD is that quarks behave as if they are free at short distances, but are permanently confined at large distances. This statement is not philosophical. It is a concise description of decades of data. The issue, then, is not whether gluons exist. Their influence is everywhere. The deeper issue is why nature is structured so that the carriers of the strongest force can never appear alone. One possibility is stability. If color charge could propagate freely over large distances, the structure of matter would change dramatically. Another possibility lies in symmetry. The SU-3 structure at the heart of QCD forces gluons to interact with one another. Once that interaction exists, confinement follows naturally in every realistic calculation. What remains striking is the consistency. Across energy scales, experimental methods, and environments, the same pattern holds. Gluons reveal themselves only through structure, never through isolation. This constraint shapes everything that follows. If a gluon cannot exist on its own, then it cannot be understood as an isolated object in the usual sense. Its reality appears only through interaction, embedded within a wider physical framework, rather than standing apart from it. Part 2. Why would galaxies fly apart if we only count the matter we can see? If we add up every star we can photograph, every cloud we can map, every bright knot of gas we can measure, The math says many spiral galaxies should not survive their own rotation. They should shed their outer stars the way a fast spinning wheel sheds mud. Yet, the night sky is full of spiral disks that have held together for billions of years, turning steadily, refusing to come apart. The discomfort here is simple and physical. Gravity from the visible matter is not enough, and the mismatch is not small. To see why this became a crisis, it helps to imagine what a galaxy would look like if almost all its mass were where the light is. In that case, the inner region would dominate the gravitational pull. Farther out, stars would feel less inward pull, and their orbital speeds would fall with distance. The same pattern you see in the outer solar system, where planets move more slowly the farther they are from the Sun. That expectation is not a stylistic preference. It is the direct consequence of how gravity behaves for a mass concentrated toward the center. But when astronomers began to measure real galaxies carefully, the outer parts refused to cooperate. Instead of slowing down, many outer stars kept orbiting at nearly the same speed as stars much closer in. This is what people mean by a flat rotation curve, a graph that stays high instead of dropping. If you only allow the gravity of the luminous matter, the outer disk should be fragile. If you accept the observed speeds, then the galaxy must be sitting inside a much larger reservoir of mass that does not shine. The measurements did not arrive as a single cinematic moment. They arrived as long nights, careful calibration, and the patient removal of excuses. In the late 1960s and 1970s, Vera Rubin and Kent Ford used sensitive spectrographs to measure how fast parts of galaxies were moving by reading tiny shifts in the light. A Doppler signature that tells you whether material is coming toward us or moving away. Their work on Andromeda and other spirals helped make the problem unavoidable, and by the late 1970s, Rubin, Ford, and collaborators published extended rotation curves showing that the implied mass kept rising with radius instead of leveling off where the visible light thinned out. If you pause on that idea, it has a sharp edge. In the outer disk of a spiral galaxy, starlight becomes faint. Gas becomes patchy. The visible inventory declines. Yet the orbital speed does not collapse the way it should if the mass were truly fading. The most economical reading is that the mass is still there, but it is not participating in the electromagnetic world in the way normal matter does. NASA summarizes this rotation curve conflict in plain language, noting that stars near the edges of galaxies move too fast to be held by the luminous matter alone. Optical measurements were only one door into the problem. Another came from radio astronomy. Neutral hydrogen emits at a wavelength of 21 centimeters, a signal that can be tracked far beyond the bright stellar disk. That matters because a galaxy often has an extended hydrogen envelope reaching into regions where starlight is weak. By measuring the Doppler shift of that 21 centimeter emission, radio astronomers could map rotation at larger radii than optical data often allowed, and the flat behavior persisted. The result was consistency across methods, instruments, and wavelengths. It was not one team with a quirky telescope. It was the same story told in different languages of light. Now the logic becomes hard to avoid. A star in a circular orbit is not choosing its speed. It is balancing inward gravitational pull against its tendency to move straight ahead. If the inward pull is too weak, the orbit cannot be stable at that speed. In a spiral galaxy, we can measure the speed from spectroscopy. We can estimate the visible mass from starlight and gas maps. And we can test whether that visible mass could provide the necessary inward pull. In many galaxies, it cannot. So either gravity behaves differently on those scales, or there is extra mass that does not shine. The reason this became hard evidence is that rotation curves are not subtle. The discrepancy is large, systematic, and present across many types of galaxies. Some galaxies are bright and massive, some are faint and diffuse, some are rich in gas, some are dominated by old stars. Yet the pattern of missing mass repeats. When astronomers turned this into a working model, they did not imagine a small correction. They had to add an extended halo, a roughly spherical distribution of unseen mass surrounding the luminous disk, providing extra gravitational pull at large radii. This is the moment where dark matter stops sounding like an optional patch and starts sounding like architecture. A spiral disk is a dynamically delicate system. Stars move in ordered rotation, but the disk is also subject to instabilities. If the mass were only in the luminous disk, many galaxies would be more vulnerable to tearing, heating, and disruption. A halo changes the stability conditions. It deepens the gravitational potential well, it helps maintain rotational support, and it changes how the disk responds to disturbances. When astronomers speak about galaxy stability, they are not being poetic. They mean whether a rotating disk can persist without being shredded by its own motion or by gravitational interactions. A useful way to feel the depth of the problem is to remember what "we can see" actually means. Most of the matter we directly observe in a galaxy is luminous stars and gas traced through emission or absorption. We can estimate the mass in stars by measuring brightness and colors, applying stellar population models, and calibrating those models using nearby stars. We can estimate gas mass using radio lines like hydrogen 21 centimeter and molecular tracers like carbon monoxide. These methods carry uncertainties, but they are not free to drift anywhere they want. They are tied to physical measurements, to spectra, to well-tested calibrations, and to multiple independent surveys. The missing mass problem survives those uncertainties. This is also why the problem sharpened over time, rather than dissolving. Early on, one could hope that astronomers were misjudging how much ordinary matter was present, perhaps hidden in dim stars or cold gas. But as surveys improved, as infrared astronomy mapped cooler components, as radio telescopes traced hydrogen more completely, and as stellar population modeling became more constrained, the gap remained. The outer orbital speeds were still too high for the visible inventory. At this point, a skeptical mind should ask something concrete. If unseen mass is really there, does it behave in a way that is consistent across the universe, or is it just a word we use when we get confused? Here the evidence broadens. Dark matter is not inferred from rotation curves alone. It appears in galaxy clusters through gravitational lensing and galaxy motions, and it appears in the cosmic microwave background through the imprint of early universe physics. The rotation curve evidence is powerful because it is local and mechanical. It involves objects moving in the present universe under gravity in a regime where Newtonian intuition is usually reliable. The calm but relentless conclusion is that a spiral galaxy is not just a bright disk floating in emptiness, it is a bright disk embedded in something much larger. When you look at a spiral galaxy image, most of the mass is not in the part your eyes are drawn to. The luminous matter is the tracer, not the main reservoir. NASA's framing is blunt, and it is meant to be. Something unseen is tugging on galaxies and holding them together. This is where it helps to connect rotation curves to the broader census of the universe. The European Space Agency's Planck mission measured the cosmic microwave background with high precision and derived a composition in which normal matter is a small fraction of the total, while dark matter accounts for about 26.8% of the universe's mass-energy budget. The number matters here because it shows that the missing mass in galaxies is not an isolated bookkeeping error. It fits into a consistent cosmic inventory drawn from early universe data. None of this forces a single interpretation. There are alternatives that modify gravity rather than adding unseen matter, and those alternatives are taken seriously because they make testable predictions. The point is that rotation curves created a crisis that demanded a structural explanation, not a cosmetic one. The crisis is that galaxies rotate as if extra mass is present. The structural move is that galaxies are embedded in halos that dominate their gravitational fields at large radii. There is also a practical reason rotation curves became persuasive. They offer a clean relationship between what you measure and what you infer. You measure velocity as a function of radius. That velocity profile tells you the enclosed gravitational influence. If the enclosed influence keeps growing with radius, even when the light falls off, something must be contributing. It can be unseen mass, or it can be new gravitational behavior. Either way, the galaxy is telling you that the visible matter is not the full story. The historical texture matters too, because scientific crises are not solved by one graph. They are solved when competing teams, using different tools, repeatedly find the same mismatch. Rubin's optical work became one pillar. Radio maps of hydrogen became another. Later, large surveys multiplied the sample size from a handful of galaxies to thousands. The missing mass pattern did not fade as statistics improved. It became more mapped, more categorized, and more difficult to dismiss. If you want a short, sharp way to hold on to this, keep it mechanical. In the outer parts of many spirals, stars orbit too fast for the visible mass to keep them bound. If the visible mass were all there is, the disk would loosen and disperse. It does not. Therefore, either there is extra gravitational source in the form of unseen mass, or our law of gravity changes in that regime. The observation comes first. The theory must follow it. And now the next pressure builds on its own. If galaxies require an unseen component to stay intact, then the universe should also carry that component through cosmic history, shaping how structure formed, how early galaxies assembled, and how the cosmic web grew from small fluctuations into today's large-scale patterns. Because once a galaxy's rotation curve refuses to fall, the darkness is no longer a philosophical absence. It becomes an engineering requirement for the universe to build stable spirals at all. That same unseen mass does more than hold individual galaxies together. It also bends the light of distant objects behind them, producing effects that visible matter alone can never reproduce. Part 3. How does the strongest force in nature become invisible at longer distances? The most disturbing feature of the strong force is not its strength, but how completely it disappears the moment we try to look at it from afar. At the scale of quarks, it is the most powerful interaction ever measured. At the scale of atoms, molecules, or everyday matter, it leaves no direct trace at all. Something capable of binding the very heart of matter together fades so thoroughly that, beyond a certain distance, it seems not to exist. In physics, forces usually weaken as distance increases. Gravity pulls less strongly the farther two masses are separated. Electromagnetism follows the same pattern, its influence spreading outward and thinning with distance. The strong force behaves in precisely the opposite way. When two quarks are close together, the interaction between them is surprisingly mild. As they are pulled apart, the force does not weaken. It intensifies. This reversal is not an analogy or a metaphor. It is a measured property of quantum chromodynamics. The first experimental clues appeared in the late 1960s and early 1970s, when high-energy scattering experiments began probing protons at increasingly small distances. Electrons fired into protons behaved as if they were colliding with nearly free, point-like objects. This observation led to the concept of asymptotic freedom, formulated independently by David Gross, Frank Wilczek, and David Politzer in 1973. They showed that, at extremely short distances, the strong force becomes weaker, allowing quarks to move almost independently. For this work, they would later receive the Nobel Prize. That result carried an unexpected implication. If the force weakens at short distances, then it must strengthen at longer ones. The mathematics of QCD demanded it. This was not speculation. It was a consequence of how color charge behaves in a non-abelian gauge theory. Unlike electric charge, color charge comes in multiple types, and the carriers of the force themselves carry that charge. Gluons interact not only with quarks, but also with each other. This self-interaction alters how the force spreads through space. Instead of dispersing, the field lines attract one another, narrowing into a confined structure. Physicists describe this structure as a flux tube. When two quarks are close, the tube is short and contains relatively little energy. As the quarks are pulled apart, the tube stretches, storing more and more energy along its length. Measurements and simulations indicate that the energy increases roughly in direct proportion to the separation distance. There is no point at which the connection weakens enough to break cleanly. This behavior has been confirmed through decades of lattice QCD calculations. By discretizing spacetime into a grid and solving the equations numerically, physicists can calculate how the gluon field behaves as quarks are separated. The results are consistent across independent groups and computing platforms. The energy does not spread out, it concentrates. At some point, stretching the flux tube becomes energetically expensive. When enough energy accumulates, the field reorganizes itself. Instead of allowing the quarks to separate further, it produces a new quark-antiquark pair from the vacuum. The original quarks now belong to different bound systems. What looked like an attempt to isolate particles results instead in the creation of more confined matter. This is why the strong force becomes effectively invisible at larger distances. It does not fade away. It hides itself inside bound structures. Beyond the size of a proton, its influence is locked into stable particles. Outside those particles, there is nothing left to measure directly. This invisibility is not an absence. It is a consequence of confinement. The force does all its work internally, leaving only its products behind. Protons, neutrons, and other hadrons carry the imprint of the strong force in their masses and internal structure, but the force itself does not extend freely into space. Historical experiments reinforced this understanding. In the 1970s, physicists searched for deviations from expected force laws at nuclear scales. If the strong force leaked outward even slightly, it would produce measurable effects beyond the size of nuclei. None were found. Nuclear forces appeared short-ranged and saturated, consistent with confinement. Later, experiments involving jets in particle colliders added further evidence. When quarks or gluons are produced in high-energy collisions, they never appear as isolated tracks. Instead, detectors observe narrow sprays of hadrons. The angular distribution, energy flow, and internal structure of these jets match predictions from QCD that assume confinement. The force does not release particles. It reshapes them. One of the most striking confirmations came from heavy ion collisions. By colliding large nuclei at extreme energies, physicists recreated conditions similar to those that existed microseconds after the Big Bang. In this environment, quarks and gluons form a hot, dense medium known as quark-gluon plasma. Over very short distances, color charges move more freely, and the strong force behaves differently. Yet even here, as the system cools, confinement returns. The force does not propagate outward. It locks itself back into hadrons. Observations of this plasma revealed another crucial detail. The medium behaves not like a weakly interacting gas, but like a nearly perfect fluid. This behavior reflects the collective nature of gluon interactions. Even when partially deconfined, the strong force does not resemble familiar long-range interactions. It remains dominated by self-interaction and collective dynamics. The invisibility of the strong force at larger scales has profound consequences. It explains why atomic nuclei are stable and localized. It explains why matter has size and shape rather than dissolving into diffuse clouds of interacting charges. It explains why chemistry and biology can exist without being overwhelmed by nuclear interactions. From an experimental standpoint, this invisibility posed a challenge. Early physicists expected forces to reveal themselves through long-range effects. The strong force defied that expectation. Its presence had to be inferred indirectly, through scattering patterns, mass distributions, and energy flows. One of the clearest demonstrations lies in the mass of the proton. The proton's mass is far larger than the combined masses of its constituent quarks. That extra mass arises from the energy stored in the gluon field and the motion of confined quarks. The strong force, though invisible outside the proton, dominates its internal energy budget. It shapes the mass of ordinary matter while remaining hidden from direct observation. This property also explains why attempts to detect free gluons have failed. The force that binds them grows stronger with distance. Any attempt to separate them activates the very mechanism that prevents separation. The stronger the effort, the more confinement asserts itself. David Gross once described this behavior succinctly when explaining QCD to a general audience. He noted that the strong force is strong because it does not behave like other forces. It traps its own charges. This trapping is not an added rule. It is built into the structure of the theory. From a mathematical perspective, this behavior arises from the running of the coupling constant. At high energies and short distances, the coupling decreases. At lower energies and larger distances, it increases. This running has been measured experimentally and calculated theoretically with high precision. It is one of the most thoroughly tested features of the Standard Model. What makes the situation remarkable is how cleanly nature separates scales. At distances smaller than a proton, the strong force governs quark dynamics. At distances larger than a proton, its effects are frozen into composite particles. There is no gradual leakage. The transition is abrupt and complete. This separation allows other forces to dominate at larger scales. Electromagnetism governs atomic structure. Gravity governs astrophysical systems. The strong force remains confined to its domain, shaping matter at the smallest scales without interfering directly with larger structures. The story behind this understanding is one of persistence. For years, confinement was suspected but not fully accepted. Physicists searched for exceptions, loopholes, and alternative explanations. Each new experiment closed another door. Each new calculation reinforced the same conclusion. Today, confinement is not viewed as a limitation, but as an organizing principle. It explains why the strongest force does not tear matter apart. It explains why the universe can be both stable and structured. It explains why something so powerful can remain unseen. The strong force does not vanish at long distances. It completes its work and withdraws. Its invisibility is the signature of its success. If the strongest interaction in nature becomes effectively hidden beyond the scale of quarks, then its influence must reappear indirectly, shaping mass, stability, and the internal dynamics of the particles that make up everything we observe. Part 4. Why do gluons interact with each other, not just with quarks? The most disruptive fact about gluons is not that they bind quarks together, but that they refuse to limit their interactions to quarks alone. Unlike every force carrier that behaves as a neutral messenger, gluons respond to one another directly. This single property transforms the strong force from a simple exchange into a dense, self-reinforcing network that reshapes matter from the inside out. In quantum chromodynamics, gluons are defined as carriers of color charge. This immediately sets them apart from photons. Photons transmit electromagnetic force, yet they carry no electric charge themselves. Two photons can pass through one another without interaction. Gluons cannot. Each gluon carries color charge, and color charge responds to color charge. As a result, every gluon becomes both a messenger and a participant in the force it conveys. This feature was not added by choice. It emerges inevitably from the mathematical structure of the theory. QCD is built on a symmetry known as a non-abelian gauge symmetry, specifically the SU3 symmetry associated with color charge. In such a framework, the force carriers inherit the charge of the interaction. Once that symmetry is fixed, gluon self-interaction follows automatically. The consequences were not obvious when the theory was first proposed. In the early 1970s, as physicists worked to formalize the strong interaction, many expected it to resemble electromagnetism with added complexity. That expectation failed. When the equations were examined carefully, new interaction terms appeared. These terms described gluons coupling to other gluons. The force was no longer linear. It folded back on itself. David Gross, reflecting on this period, described how unexpected this behavior was. He noted that the equations were simple to write down, but their implications were anything but. Once self-interaction entered the picture, intuition built from electromagnetism no longer applied. This self-interaction explains why the strong force behaves so differently from all others. When quarks exchange gluons, those gluons interact with each other at the same time. The field does not propagate outward smoothly. It knots, twists, and reinforces itself. Energy does not dilute with distance. It concentrates. Lattice QCD calculations provide a direct window into this behavior. By solving the equations of QCD numerically on large space-time grids, physicists can visualize how gluon fields evolve. These simulations, refined over decades using international supercomputing resources supported by agencies such as NASA and ESA, show that gluon fields form dense, interconnected structures even in the absence of quarks. The field interacts with itself continuously. This insight overturned earlier assumptions. It became clear that the strong force is not mediated by isolated exchanges, but by a collective field whose components cannot be separated cleanly. Each gluon influences the behavior of the others. The result is confinement, not as an added rule, but as a natural outcome. Experimental evidence supports this picture. In high-energy collisions, Gluons reveal themselves through jet patterns that differ from those produced by quarks alone. The angular distributions and energy flows measured in detectors match predictions that include gluon self-interaction. Without these interactions, the observed patterns would be impossible to reproduce. One striking example comes from 3 jet events in electron-positron collisions. The presence of a third jet reflects gluon emission, but the internal structure of that jet carries the imprint of gluon coupling. The way energy fragments inside the jet cannot be explained unless gluons interact among themselves before confinement sets in. Heavy ion collisions deepen this understanding. When nuclei collide at extreme energies, they briefly create a medium dominated by gluons. In this environment, known as quark-gluon plasma, gluon self-interaction governs the collective behavior of the system. Measurements show that the plasma behaves like a strongly coupled fluid rather than a weakly interacting gas. This behavior arises directly from gluon-gluon interactions. Theoretical work predicted this long before it was observed. Calculations showed that at high densities, gluon self-interaction would dominate the dynamics of the plasma. When experiments at RHIC and the LHC confirmed these predictions, confidence in the non-abelian nature of QCD deepened. This network-like behavior has another consequence. Because gluons interact with each other, the strong force does not act independently at each point in space. Local changes propagate through the field in complex ways. Pulling on one part of the system rearranges the entire network. This is why attempts to isolate quarks or gluons fail so completely. Separation activates the field's internal response. The story behind this realization is one of gradual acceptance. Early resistance stemmed from habit. Physicists were accustomed to forces mediated by neutral messengers. A force whose carriers interact with one another seemed unwieldy. Yet data accumulated relentlessly. Every attempt to model the strong interaction without gluon self-interaction failed to match experiments. By the 1980s, the evidence was overwhelming. Jet studies, scaling violations in deep inelastic scattering, and lattice simulations all converged on the same conclusion. Gluons must interact with one another. Without that property, QCD would collapse as a theory. This property also explains why the strong force generates most of the mass of ordinary matter. Energy stored in interacting gluon fields contributes directly to mass. Inside a proton, gluons exchange energy not only with quarks but with other gluons continuously. The resulting energy density dominates the proton's mass budget. This means that mass is not primarily a property of constituent particles. It is a property of an interacting field. Gluon self-interaction ensures that energy remains confined, dense, and persistent. Without it, protons would be far lighter, and matter would be fundamentally different. The same mechanism governs the stability of nuclei. The strong force binds quarks into nucleons, and residual effects bind nucleons into nuclei. Gluon self-interaction ensures that this binding remains localized and robust. It prevents the force from leaking outward and destabilizing larger structures. From a broader perspective, this behavior explains why the universe can support complexity. A force that binds too weakly cannot form stable matter. A force that spreads too freely disrupts structure. The strong force, through gluon self-interaction, achieves a balance that confines its effects to the smallest scales while shaping everything built upon them. Carl Sagan once emphasized that understanding nature often requires abandoning familiar analogies. In discussing fundamental forces, he remarked, "Nature is subtle and elegant, but not malicious." In the case of gluons, subtlety lies in accepting that force carriers need not behave like messengers at all. They can be participants in a collective system. This collective behavior is now central to modern physics. It informs how simulations are built, how experiments are interpreted, and how new states of matter are predicted. It also sets limits. Any future theory that seeks to extend or replace QCD must reproduce gluon self-interaction with extraordinary accuracy. What remains striking is how much structure arises from this single feature. By carrying color charge, gluons transform the strong force into a self-coupled network. That network confines quarks, generates mass, and stabilizes matter. It does so quietly, without revealing its workings directly, leaving behind only the particles we can observe. If gluons interact so intensely with one another that they dominate the internal energy of matter, then that hidden interaction must account for most of the mass we measure in the visible universe, even when the constituent particles themselves contribute very little. Part 5. Could gluons be the real reason why protons are heavy? The most unsettling fact about the proton is that nearly all of its weight comes from something that has no weight of its own. If you add up the masses of the 3 quarks inside a proton, you recover only a small fraction of what the proton actually weighs. The rest does not come from hidden particles or unknown ingredients. It comes from energy, specifically from the energy stored in gluon fields that never leave the proton. For much of the 20th century, physicists assumed that mass worked like a ledger. You added up the masses of the constituents, and the total gave you the mass of the whole. That intuition works well for atoms, molecules, and even nuclei. It fails completely for protons. The proton has a mass of about 938 mega-electron-volts. The combined masses of its up and down quarks contribute only a few % of that value. Something else is doing the work. Quantum chromodynamics provides the explanation. Inside the proton, quarks are bound by gluons that interact intensely with one another. These interactions store enormous amounts of energy in a very small volume. According to relativity, energy contributes to mass. The proton's mass is therefore not dominated by what its quarks are, but by what they are doing and how strongly they are bound. This realization emerged gradually. In the 1960s, deep inelastic scattering experiments revealed that quarks behave as if they are nearly free when probed at extremely short distances. That discovery raised an obvious question. If quarks are almost massless and weakly interacting at short scales, where does the proton's mass come from? As theoretical understanding improved in the 1970s, the answer became clearer. The strong force weakens at short distances, but strengthens dramatically at larger ones. Inside the proton, quarks are confined to a small region by gluon fields that do not spread outward. Those fields store energy continuously. The tighter the confinement, the higher the energy density. Lattice QCD calculations provided the first quantitative confirmation. By simulating quarks and gluons on discretized spacetime grids, physicists could calculate the mass of the proton from first principles. The results were striking. When quark masses were set close to their measured values, the simulations still reproduced the full proton mass. The missing mass came from gluon energy and the motion of confined quarks. This was not a numerical trick. Independent lattice groups, using different methods and computing platforms, arrived at the same conclusion. The proton's mass is an emergent property of interacting fields. It is not a simple sum of parts. Experiments reinforced this picture. Measurements of proton structure functions showed that gluons carry a significant fraction of the proton's momentum, even though they have no rest mass. In high-energy collisions, gluon distributions dominate the proton's internal dynamics. The proton behaves less like a bag of particles and more like a dense region of interacting energy. One of the clearest demonstrations comes from studies of how momentum is shared inside the proton. As energy increases, gluons become more numerous. They split, recombine, and interact continuously. At high energies, gluons carry most of the proton's momentum. This behavior has been measured repeatedly at particle accelerators and matches QCD predictions with high precision. The story behind this understanding is also a story of changing intuition. Early models treated quarks as tiny, massive objects held together by a force. QCD replaced that picture with something less familiar. Quarks move relativistically. Gluons form a self-interacting field. Mass arises from dynamics, not from static components. This shift is captured in a remark often attributed to Carl Sagan when discussing fundamental physics. He emphasized that nature is not obliged to match human intuition, only to obey its own rules. In the proton, those rules produce mass through interaction rather than substance. The Higgs mechanism plays only a minor role here. The Higgs field gives quarks their small intrinsic masses, but those masses account for only a few % of the proton's total. Turning off gluon interactions would remove most of the proton's weight, even if the Higgs field remained unchanged. This distinction is essential. The origin of mass in everyday matter is not the same as the origin of mass for fundamental particles. This has been confirmed indirectly through studies of how protons behave under extreme conditions. In heavy ion collisions, when quark-gluon plasma forms, confinement weakens temporarily. As the plasma cools and confinement returns, mass re-emerges in the form of hadrons. The process converts energy stored in fields into the mass of particles. Observations of this transition align with QCD predictions. Astrophysical evidence is consistent as well. The mass of stars, planets, and living organisms is dominated by protons and neutrons. If gluon energy did not contribute to mass, the universe would be dramatically lighter. Stellar evolution, gravitational collapse, and cosmic structure would all look different. The fact that they do not reflects the central role of gluon dynamics. From a theoretical standpoint, this understanding resolved a long-standing puzzle. It explained why protons are heavy even though their constituents are light. It also clarified why mass is stable. Gluon interactions are confined. Their energy cannot leak away. As long as confinement holds, mass persists. This confinement also explains why protons do not decay under normal conditions. The energy that gives them mass is locked inside. There is no channel for it to escape without violating the rules of QCD. Stability follows naturally. What makes this story especially compelling is its economy. No new particles are required. No hidden mechanisms are invoked. The same gluons that bind quarks also generate mass. One interaction accounts for two fundamental properties of matter. The implications extend beyond protons. Neutrons, mesons, and other hadrons follow the same pattern. Their masses reflect the energy of interacting gluon fields. Differences arise from how quarks are arranged and how strongly fields interact, not from large differences in quark masses. This perspective also reshapes how physicists think about weight. Mass is not a measure of how much matter is present, but of how much energy is confined. Inside the proton, that energy is enormous relative to the size of the system. The proton's radius is about 0.8 femtometers, yet it contains nearly a giga-electron-volt of energy. The density is extreme. This density is not uniform. Gluon fields fluctuate, concentrate, and redistribute energy continuously. These fluctuations contribute to the proton's properties, including its spin and internal pressure distribution. Recent experiments mapping the internal forces inside the proton reveal pressures far greater than those found in neutron stars, all generated by gluon interactions. The history of these discoveries underscores the power of careful measurement. No single experiment revealed the answer. It emerged from decades of scattering data, theoretical work, and computational advances. Each piece reinforced the same conclusion from a different angle. Today, the idea that most mass comes from gluon energy is no longer controversial. It is built into modern physics textbooks and confirmed by precision calculations. Yet, it remains counterintuitive. We live in a world where solidity feels fundamental. The proton teaches a different lesson. Weight comes from motion, confinement, and interaction. This understanding also places limits on future theories. Any extension of the standard model must reproduce the proton's mass with the same accuracy. It must account for how gluon self-interaction generates energy, and how that energy becomes mass. There is little room for error. The deeper significance is practical as well as conceptual. Technologies that rely on nuclear physics, from energy generation to medical imaging, depend on the stability and mass of hadrons. That stability is a direct consequence of gluon dynamics. Seen this way, the proton is not heavy because it contains heavy things. It is heavy because it is busy. Its interior is a constant exchange of energy among quarks and gluons, confined so tightly that energy becomes mass. If mass emerges primarily from gluon interaction rather than from substance, then the gluon itself cannot be treated as an ordinary particle. Its presence appears only as a temporary excitation within quantum fields, with no independent existence outside interaction. Part 6. What happens when gluons and quarks are liberated in extreme conditions? The most unsettling realization in modern nuclear physics is that protons and neutrons can completely lose their identity when matter is heated or compressed far enough. The particles that feel solid and indivisible, under ordinary conditions, dissolve into something else entirely, a state where quarks and gluons are no longer confined, and the familiar boundaries of matter simply fail to hold. Under normal conditions, quarks and gluons are locked inside hadrons by confinement. Their interactions are so strong that isolation is impossible. But quantum chromodynamics also predicts a limit. When temperature or density rises beyond a critical threshold, confinement weakens. The force that usually traps quarks and gluons rearranges itself. Matter enters a new phase, known as quark-gluon plasma. This is not a speculative idea. It is a direct consequence of QCD, supported by theory, numerical simulation, and experiment. Lattice QCD calculations show that at temperatures of roughly 2 trillion Kelvin, the energy density becomes high enough to disrupt the confined structure of hadrons. At this point, quarks and gluons are no longer bound into individual protons and neutrons. They move within a shared medium. The first place this state existed was the early universe. According to cosmological models, during the first few microseconds after the Big Bang, the universe was too hot for protons or neutrons to exist. Matter was a dense, rapidly expanding plasma of quarks, gluons, electrons, and photons. As the universe expanded and cooled, confinement emerged. Quarks became locked into hadrons. The familiar building blocks of matter formed only after this transition. For decades, this early phase of the universe remained inaccessible. No telescope could see that far back. Even today, instruments such as the James Webb Space Telescope observe the universe long after this transition occurred. The quark-gluon plasma era left no direct light behind. Understanding it required recreating similar conditions on Earth. That effort began in earnest in the late 20th century. Particle accelerators capable of colliding heavy nuclei at extreme energies were built to compress matter to extraordinary densities. By smashing nuclei together at nearly the speed of light, physicists could momentarily reproduce energy densities similar to those of the early universe. Facilities such as the relativistic heavy ion collider and later the Large Hadron Collider were designed with this goal. When gold or lead nuclei collide head-on, hundreds or thousands of particles emerge. But the most important signals are not individual particles. They are collective patterns that reveal the properties of the medium formed in the collision. Early expectations assumed that quark-gluon plasma would behave like a weakly interacting gas. If quarks and gluons were freed, it seemed reasonable to expect them to move independently. The data told a different story. Measurements showed that the plasma behaves like a nearly perfect fluid, with extremely low viscosity. Instead of free particles, the system exhibits strong collective motion. This result surprised the field. The liberated quarks and gluons still interact intensely with one another. Confinement weakens, but gluon self-interaction remains dominant. The plasma flows, responds to pressure gradients, and redistributes energy rapidly. The strong force does not disappear. It changes its form. One of the clearest signatures comes from jet quenching. In high-energy collisions, energetic quarks or gluons normally produce narrow jets of particles. When such jets pass through quark-gluon plasma, they lose energy rapidly. The medium absorbs and redistributes that energy. Detectors observe jets that are distorted, broadened, or even partially absorbed. This energy loss reveals how dense and interactive the plasma is. Another key observation involves collective flow patterns. Particles emerging from heavy ion collisions show correlated motion, reflecting pressure gradients in the early stages of the plasma. These patterns match predictions from hydrodynamic models that assume a strongly coupled fluid. The agreement between theory and experiment is striking. Behind these discoveries lies a careful chain of reasoning. Physicists do not observe quark-gluon plasma directly. They infer its properties from thousands of correlated measurements. Particle yields, momentum distributions, angular correlations, and energy flow all contribute pieces of evidence. Together, they form a consistent picture. Lattice QCD provides an independent check. By calculating the thermodynamic properties of strongly interacting matter, physicists can predict the temperature at which confinement breaks down. These predictions match the conditions inferred from experiments. The transition is not sharp like melting ice, but it is well defined. The story of quark-gluon plasma is also a story of technological progress. Early accelerators lacked the energy and precision needed to study this state. Advances in detector design, computing, and data analysis made it possible to extract subtle signals from complex events. International collaborations spanning decades refined their methods, improving confidence in the results. What emerges is a view of matter under extreme conditions that challenges intuition. Liberation does not mean simplicity. Even when quarks and gluons are no longer confined into hadrons, they do not behave as isolated objects. The strong force remains active, shaping the medium as a whole. This behavior has profound implications for the early universe. During the quark-gluon plasma era, matter behaved as a collective system. As the universe expanded and cooled, confinement emerged smoothly. Quarks locked into hadrons. Gluons became confined. The energy stored in the plasma reorganized itself into the mass of particles. This transition set the stage for everything that followed. Without it, protons and neutrons would not exist. Without protons and neutrons, nuclei would not form. Without nuclei, atoms, stars, and planets would be impossible. The structure of the universe depends on how quark-gluon plasma cooled and confined. Astrophysical environments may still contain matter under similar conditions. The cores of neutron stars reach densities far beyond those found in atomic nuclei. Some models suggest that quark matter or related phases could exist in their interiors. Observations of neutron star mergers and gravitational waves provide indirect clues, though the details remain uncertain. What is clear is that QCD governs matter across an extraordinary range of conditions. From the interior of protons to the earliest moments of the universe, the same underlying rules apply. Quark-gluon plasma is not an exotic exception. It is a natural phase of matter under extreme conditions. This realization reshaped nuclear physics. The field expanded from studying static particles to studying phases of matter. Concepts from fluid dynamics, thermodynamics, and statistical physics became central. The strong force revealed itself not only as a binding mechanism, but as a driver of collective behavior. Carl Sagan often emphasized that understanding the universe requires following evidence wherever it leads, even when it contradicts expectation. The quark-gluon plasma did exactly that. It showed that liberation does not erase interaction. It transforms it. The experiments that revealed this state did not provide a single dramatic moment of discovery. Instead, they built a case piece by piece. Each measurement added weight to the conclusion. Each refinement sharpened the picture. The result is now one of the most robust findings in high-energy nuclear physics. From a broader perspective, quark-gluon plasma teaches a precise lesson. Matter is not defined solely by its particles, but by how those particles interact under given conditions. Change the conditions enough, and matter reorganizes itself completely. The strong force allows this transformation because it is flexible. It confines at low energy. It collectivizes at high energy. It governs stability and change with the same rules. In a liberated state, quarks and gluons no longer behave as discrete objects at all. What emerges instead is a collective pattern, where fields and fleeting excitations carry the physical reality, and interaction defines what can be observed. Part 7. Is a gluon a particle, or just an excitation of a field? The most unsettling feature of a gluon is that it cannot be pointed to as a thing in the usual sense, even though its effects dominate the structure of matter. Every experiment that reveals a gluon does so indirectly, through patterns of energy, momentum, and correlation. Nothing ever appears that can be cleanly separated, stored, or observed at rest. This forces a deeper look at what physicists actually mean when they say the word particle. In modern physics, the idea of a particle is very different from the small, solid objects imagined a century ago. Quantum field theory replaces that picture with fields that exist everywhere, all the time. What we call a particle is a localized excitation of one of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. In this framework, gluons are excitations of the color field described by quantum chromodynamics. This distinction matters because the color field behaves unlike any other known field. It does not allow its excitations to exist independently. A photon can propagate freely through space because the electromagnetic field is linear and its excitations do not interact strongly with one another. The color field is non-linear. Its excitations interact with each other continuously. That interaction reshapes what it means for a gluon to exist at all. The foundations of this view were laid in the middle of the 20th century, when quantum field theory was extended to describe forces through symmetry principles. The strong interaction required a symmetry more complex than that of electromagnetism. This symmetry, known as SU3, organizes how color charge behaves. Once this symmetry is imposed, gluons appear naturally as the quanta of the color field. What follows from that symmetry is unavoidable. Because the symmetry is non-abelian, the field interacts with itself. The equations describing it contain terms where one gluon influences another directly. These terms are not optional. They are required for the theory to remain consistent and predictive. As a result, a gluon cannot be treated as a free ripple moving through an otherwise passive medium. This became clear as soon as physicists tried to calculate what a free gluon should look like. In principle, quantum field theory allows the definition of a particle state only when the field becomes non-interacting at large distances. For gluons, this condition is never met. The interaction strength grows as distance increases. The field never settles into a regime where a single excitation can be isolated. This is why the question of whether a gluon is a particle does not have the same answer as it does for an electron or a photon. A gluon is real, but its reality is inseparable from interaction. It exists only as part of a larger dynamical system. Experimental evidence supports this view at every level. When particle accelerators produce conditions energetic enough to create gluons, detectors never see isolated tracks corresponding to gluons. Instead, they observe jets of hadrons whose internal structure reflects the presence of gluon excitations. The gluon reveals itself through correlations, not through direct detection. The three jet events observed in electron-positron collisions are a classic example. One jet corresponds to a quark, one to an antiquark, and the third carries the signature of a gluon. Yet that gluon jet is not a single object. It is a cascade of particles produced as the color field reorganizes itself. The gluon appears as a pattern, not as a particle in isolation. Lattice QCD calculations deepen this understanding. By solving the equations of QCD numerically on discretized spacetime, physicists can study the behavior of gluon fields without relying on perturbative approximations. These calculations show that gluon excitations are highly delocalized and strongly coupled. They do not resemble independent entities. They resemble fluctuations of a tightly bound field. This picture also explains why gluons contribute so strongly to mass and pressure inside hadrons. Energy stored in interacting fields contributes to mass. Because gluons interact with each other continuously, the energy density inside a proton is dominated by gluon dynamics. The proton's mass reflects the behavior of the field, not the presence of massive constituents. The idea that particles are excitations rather than objects has historical roots. Early quantum theorists struggled with the wave-particle duality of light and matter. Over time, field theory provided a unifying language. In that language, waves and particles are two ways of describing the same underlying reality. For gluons, the wave description is essential. The particle picture is only approximate and often misleading. This realization resolved several puzzles at once. It explained why free gluons are never observed. It clarified why confinement arises naturally. It showed why gluon self-interaction dominates the strong force. All of these features follow from treating gluons as field excitations rather than as independent objects. The behavior of quark-gluon plasma reinforces this view. In that extreme state of matter, quarks and gluons move over short distances with reduced confinement. Yet, even there, gluons do not appear as free particles. The medium behaves collectively. Energy and momentum flow through the field as a whole. Individual excitations are short-lived and strongly coupled. This collective behavior was unexpected. Many physicists initially assumed that liberating quarks and gluons would produce something like a gas of particles. Instead, experiments showed a strongly coupled fluid. This outcome aligns naturally with a field-based description. When excitations interact strongly, the field itself becomes the primary actor. Theoretical work predicted this long before it was observed. Calculations showed that at high temperature and density, the color field would still exhibit strong correlations. The excitations would not decouple. The plasma would behave as a collective system. Experimental confirmation strengthened confidence in the field-based interpretation. The distinction between particle and field also clarifies why gluons resist localization. To localize an excitation, one must isolate it from its surroundings. For gluons, isolation increases interaction. The more one tries to separate a gluon, the more the field responds. The attempt to localize destroys the conditions required for a particle-like description. This is not a failure of measurement. It is a property of the theory. Quantum chromodynamics does not permit a gluon to exist as an asymptotic free state. The mathematics forbids it. Carl Sagan often emphasized that scientific progress requires refining the language we use to describe nature. He noted that familiar words can mislead when applied beyond their domain of usefulness. The word particle is one such case. For gluons, it is a convenience, not a literal description. Understanding gluons as field excitations also aligns with how modern physics treats all fundamental interactions. Fields are primary, particles are manifestations. This perspective unifies diverse phenomena under a common framework. It also sets boundaries. Any theory that aims to go beyond QCD must reproduce this behavior. It must explain why gluon excitations cannot exist independently and why their effects are nevertheless measurable with extraordinary precision. The practical implications are significant. Simulations of nuclear matter, predictions of collider outcomes, and interpretations of astrophysical observations all rely on this field-based understanding. Treating gluons as independent particles would lead to incorrect results. What emerges is a coherent picture. A gluon is not a small object flying between quarks. It is a localized excitation of a self-interacting field. Its existence is inseparable from the environment in which it appears. It cannot be extracted without destroying the conditions that define it. This perspective does not diminish the reality of gluons. It sharpens it. Gluons are real because their effects are real, measurable, and consistent. Their reality is encoded in interaction, not isolation. When gluons are treated as transient excitations of a field, attention shifts to how that field reorganizes itself as matter forms, breaks apart, and recombines. Those processes leave measurable signatures behind, even when the excitations themselves never appear in isolation. Part 8. Why doesn't the glue that binds quarks ever let them go? The most unsettling feature of the strong interaction is not that it binds quarks together, but that every attempt to pull them apart produces more matter instead of freedom. No matter how much energy is applied, no matter how violent the collision, quarks never emerge alone. The force that binds them does not weaken, does not snap, and does not release. It responds by transforming tension into new particles. In everyday experience, pulling something hard enough eventually breaks it. Bonds stretch, thin, and fail. For the strong force, this intuition fails completely. Quantum chromodynamics predicts, and experiments confirm, that the energy stored between separating quarks increases steadily with distance. There is no regime where the interaction fades. The farther quarks are pulled apart, the more energy accumulates in the gluon field connecting them. This behavior was not obvious when quarks were first proposed. Early models imagined quarks bound by forces similar to electromagnetism, just stronger. That picture quickly ran into contradictions. If the force behaved like electromagnetism, sufficiently energetic collisions should have liberated free quarks. They never did. The turning point came when physicists understood that the strong force does not spread out through space. Instead, the gluon field concentrates itself into narrow regions. As quarks separate, the field does not dilute, it tightens. Energy becomes localized rather than dispersed. Lattice QCD calculations made this explicit. When quarks are placed on a numerical space-time grid and slowly separated, the energy of the system rises almost linearly with distance. This result has been reproduced by independent research groups for decades. The pattern is robust. It does not depend on computational details or approximations. The theory itself demands it. As separation continues, the system reaches a critical point. The energy stored in the gluon field becomes sufficient to create a new quark-antiquark pair from the vacuum. This process does not require external matter. It follows directly from the rules of quantum field theory. Energy can convert into particle-antiparticle pairs when enough energy is concentrated in a small region. When this happens, the original quarks do not escape. Instead, the system reorganizes. Each original quark pairs with one of the newly created quarks or antiquarks. Two bound systems replace one stretched connection. The number of confined particles increases, but none are freed. This process is known as hadronization. It is not an occasional outcome. It is the default response of the strong force to separation. Every high-energy collision observed in particle detectors shows the same pattern. Energetic quarks and gluons never appear as isolated tracks. They fragment into jets of hadrons, reflecting the repeated conversion of field energy into matter. The experimental evidence is extensive. In electron-positron collisions, quark-antiquark pairs are produced with high energies. Detectors never observe those quarks directly. Instead, they observe sprays of hadrons emerging along the directions of the original quarks. The distribution of particles within these jets matches detailed predictions from QCD models of hadronization. The same behavior appears in proton-proton collisions and heavy ion collisions. Regardless of the environment, confinement reasserts itself as soon as energy is redistributed. Even in quark-gluon plasma, where confinement is temporarily weakened, cooling restores the same outcome. Quarks and gluons reorganize into hadrons. Behind this behavior lies a key difference between the strong force and other interactions. In electromagnetism, force carriers do not interact with each other. Field lines spread outward, weakening with distance. In QCD, gluons interact with one another. Their self-interaction prevents the field from dispersing. Energy remains localized. This self-interaction is not a detail. It is central. It ensures that pulling on one part of the system affects the entire field. Separation triggers a collective response. The system resists isolation by creating new structures. The historical search for free quarks highlights how firmly this rule is enforced. In the 1970s and 80s, physicists searched cosmic rays, lunar samples, and accelerator debris for particles with fractional electric charge. If quarks could ever exist freely, even briefly, traces might appear. None were found. The absence was systematic across environments and detection methods. This absence was not treated lightly. Experiments improved sensitivity repeatedly. Limits tightened. Still, nothing appeared. Over time, the conclusion became unavoidable. The strong force does not permit free color charge. Theoretical work reinforced this conclusion. Models that attempted to soften confinement failed to match observations. Only theories that preserved energy growth with separation reproduced experimental data. Confinement emerged as a non-negotiable feature of QCD. The implications extend beyond particle physics. Confinement explains why nuclear forces are short-ranged. Although the strong force is powerful, it does not leak beyond hadrons. Outside a proton or neutron, its influence is effectively sealed. This allows atoms to exist without being torn apart by nuclear interactions. This sealing is not accidental. It is a direct consequence of how energy behaves in the gluon field. Because energy is converted into matter before it can propagate outward, the force remains localized. It completes its work internally and leaves stable structures behind. This behavior also explains why attempts to measure the strong force directly at long distances fail. There is nothing to measure. The force does not act between separated objects. It acts only within confined systems. The story of confinement is therefore not one of hidden particles, but of prevented outcomes. Nature does not hide quarks and gluons behind technical barriers. It forbids their isolation through the structure of its laws. This realization reshaped how physicists think about force. A force need not weaken with distance to be stable. It can instead reorganize energy to prevent separation altogether. In QCD, tension is not released. It is transformed. The mathematics of the theory reflects this transformation precisely. When the equations are examined carefully, the solutions corresponding to isolated color charges are unstable. The system naturally evolves toward configurations where color charge is neutralized locally. Stability follows from confinement. This explains why hadrons always appear in color-neutral combinations. Protons, neutrons, and mesons carry no net color charge. The strong force enforces this neutrality relentlessly. Any attempt to violate it triggers particle production. The process is efficient. It happens on timescales far shorter than detection resolution. By the time particles reach detectors, confinement has already reshaped the event. What is observed are hadrons, not the quarks or gluons that initiated the interaction. Carl Sagan often emphasized that nature's rules reveal themselves through consistency. In the case of confinement, that consistency spans energy scales, environments, and experimental techniques. The same outcome appears everywhere. The strong force does not allow partial freedom. It does not permit exceptions. It responds to separation with creation, not release. This behavior also sets boundaries for future theories. Any theory that extends or replaces QCD must preserve confinement with extraordinary precision. Even small deviations would produce observable free color charge. None has been seen. From a practical standpoint, confinement underlies the stability of matter. Without it, protons would not be stable. Without stable protons, chemistry and biology would be impossible. The everyday solidity of the world depends on a force that never lets go. Seen this way, the glue that binds quarks does exactly what it must. It does not break, it reorganizes. It converts tension into structure. In high-energy experiments, detectors never record gluons at all. What they capture instead are sprays of particles, uneven energy distributions, and characteristic patterns that repeat from one collision to the next. Those patterns are the only place where gluons leave their mark. Part 9. What does the experimental evidence really say about gluons? The most unsettling truth about gluons is that every piece of experimental evidence for their existence is indirect, and yet the evidence is so consistent, so redundant, and so precise that removing gluons from modern physics would cause the entire experimental record of high-energy collisions to collapse at once. We have never seen a free gluon, but we have seen its consequences so many times, in so many different ways, that its presence is unavoidable. In experimental physics, reality is not defined by visibility. It is defined by repeatable effects. Gluons earn their place in the standard model not because they appear in detectors as isolated tracks, but because without them, decades of measurements would make no sense. The first serious experimental clues came from electron-positron collisions, where initial conditions are unusually clean. When an electron and a positron collide, they annihilate into pure energy. That energy then reorganizes itself into new particles. There are no messy composite projectiles to complicate interpretation. What emerges is governed directly by the underlying interaction rules. In the early 1970s, experiments showed that these collisions typically produced two narrow jets of particles moving in opposite directions. This was exactly what quantum chromodynamics predicted if a quark and an antiquark were created and then confined into hadrons. The pattern was clean, symmetric, and repeatable. But as collision energies increased, something new appeared. In 1979, experiments at the Petra Collider in Germany observed events with 3 distinct jets instead of 2. The geometry was unmistakable. 2 jets behaved like quarks. The third carried momentum, angular distribution, and energy flow that could not be explained by quark motion alone. The only consistent explanation was the emission of a gluon. This was not a matter of interpretation preference. Competing models were tested. Without gluons, no alternative theory could reproduce the observed angular correlations. With gluons, the predictions matched the data quantitatively. That moment marked the first direct experimental confirmation of the gluon as a real physical entity, not visible as a particle, but visible as a pattern. The importance of 3-jet events goes deeper than simple detection. The internal structure of those jets carried additional information. Jets associated with gluons were broader and contained more particles than jets associated with quarks. This difference arises from gluon self-interaction. Gluons radiate more readily than quarks because they carry color charge themselves. Detectors did not need to see gluons directly. They only needed to measure how energy fragmented. The fragmentation patterns matched QCD predictions with remarkable precision. As accelerators improved, evidence accumulated rapidly. Experiments measured how jet shapes changed with energy. They measured how often 3-jet events occurred compared to 2-jet events. They measured how momentum was distributed inside jets. Each measurement tested a different aspect of gluon behavior. All of them agreed. Deep, inelastic scattering experiments provided another line of evidence. When high-energy electrons are fired into protons, the scattering pattern reveals how momentum is distributed among the proton's constituents. These experiments showed that a large fraction of the proton's momentum is carried by electrically neutral constituents. Quarks alone could not account for this. Gluons were required. As energy increased, the fraction of momentum carried by gluons increased as well. This behavior matched the equations of QCD exactly. Gluons multiply at high energies through splitting processes, and experiments confirmed that multiplication. At facilities such as CERN, proton-proton collisions extended this evidence dramatically. The Large Hadron Collider produces collisions energetic enough to probe gluon dynamics directly. Most of the interactions inside the LHC are actually gluon collisions. Quarks often play a secondary role. This fact alone is striking. The dominant contributors to high-energy collision processes are particles that can never be isolated. Evidence for gluons also comes from scaling violations. Early experiments expected certain scattering distributions to remain constant with energy if quarks behaved as free particles. They did not. Subtle deviations appeared. Those deviations were predicted by QCD as the effect of gluon emission and absorption. When calculations included gluons, the deviations matched the data. Without gluons, the deviations would have been inexplicable. Heavy ion collisions added another layer. When nuclei collide at extreme energies, detectors observe collective phenomena that cannot be explained by quark interactions alone. Energy loss, flow patterns, and jet suppression all point to a dense medium dominated by gluon dynamics. One of the most telling signals is jet quenching. High-energy jets passing through quark-gluon plasma lose energy rapidly. The amount of energy lost depends on the density and interaction strength of the medium. Measurements show that this energy loss matches predictions based on gluon-dominated matter. The gluon leaves its mark not as a particle, but as resistance. There is also evidence from quarkonium suppression. Bound states of heavy quark-antiquark pairs dissolve in quark-gluon plasma. The pattern of suppression depends sensitively on the properties of the gluon field. Observations match theoretical expectations derived from QCD. Even outside collider environments, gluons leave measurable fingerprints. The mass of the proton is 1. Precision lattice QCD calculations show that removing gluon interactions from the theory removes most of the proton's mass. Experiments confirm the proton's mass with extraordinary accuracy. The agreement is not coincidental. Spin measurements offer another example. Experiments studying how the proton's spin arises show that gluons contribute significantly to total spin. This contribution has been measured directly through polarized scattering experiments. Once again, the data agree with QCD predictions involving gluons. What makes this body of evidence compelling is its diversity. No single experiment proves the existence of gluons. Thousands of experiments, using different methods, energies, detectors, and observables, all require them simultaneously. This is how experimental physics builds confidence. Independent paths converge. There is also negative evidence. Despite decades of increasingly sensitive searches, no experiment has ever detected a free gluon or free color charge. Detectors capable of seeing single electrons or photons at extreme precision see nothing corresponding to isolated gluons. This absence is exactly what QCD predicts. The consistency between presence and absence is crucial. Gluons appear where they should and disappear where they must. Historically, this pattern forced a shift in how physicists think about evidence. The gluon taught the field that direct detection is not the only form of confirmation. Structure, correlation, and consistency can be just as decisive. Carl Sagan often emphasized that science advances not by single dramatic observations, but by the quiet accumulation of consistent evidence. The gluon is a perfect example. It entered physics not as a flash of light on a detector screen, but as a necessity demanded by data. Every time a jet forms with the wrong shape for a quark, a gluon is implied. Every time momentum inside a proton exceeds what quarks can carry, a gluon is required. Every time energy loss in dense matter exceeds quark predictions, gluons must be involved. Remove gluons from the equations, and the experimental record fractures. This is why physicists say gluons are established beyond reasonable doubt. Not because they are seen, but because without them, nothing fits. The lesson here is precise. Nature does not promise that its fundamental components will present themselves in simple ways. Sometimes they announce themselves only through patterns, through constraints, through what cannot happen without them. Gluons are known by their effects, and those effects are everywhere. Gluons are essential to everything we measure inside matter, yet they never appear as isolated objects in any experiment. Their presence is inferred only through consistent, repeatable structures that emerge across theory and observation alike. Part 10. Could gluons be nothing more than a deep pattern in nature? The most unsettling possibility raised by everything we have seen so far is that gluons may not be objects at all in the way we instinctively imagine, but manifestations of a deeper organizing principle that governs how matter, force, and energy arrange themselves in the universe. After decades of experiments, simulations, and theoretical work, gluons remain real, measurable, and indispensable, yet always inaccessible as independent entities. This combination forces a final step in understanding, one that moves beyond particles as standalone things and towards structure as the primary reality. Quantum chromodynamics describes gluons as carriers of the strong interaction, but that description alone does not capture their full role. The theory is built on symmetry, specifically a symmetry that dictates how color charge behaves. Once that symmetry is chosen, gluons appear automatically, not because nature selected them as building blocks, but because the structure of the rules demands their presence. In this sense, gluons are not added ingredients. They are consequences. This perspective becomes clearer when comparing QCD with other forces. In electromagnetism, photons arise from a simple symmetry associated with electric charge. The resulting field is linear, and its excitations can exist independently. In QCD, the symmetry is more complex. The field interacts with itself. Its excitations are inseparable from the network of interactions that define them. Gluons exist because the symmetry exists, and they behave the way they do because the symmetry allows no alternative. This realization did not emerge all at once. In the early years of particle physics, forces were modeled as exchanges between particles. The success of this picture in electromagnetism encouraged physicists to extend it to the strong interaction. The extension worked mathematically, but it brought surprises. The force carriers did not behave as neutral messengers. They carried the charge of the force itself. That single feature reshaped everything that followed. As experiments accumulated, it became impossible to ignore that gluons could never be isolated. The evidence was not subtle. Every accelerator, every collision energy, every detection method reinforced the same conclusion. Free gluons do not appear, not because they are hidden, but because the theory does not permit them to exist as free states. This is where the idea of pattern becomes essential. In modern physics, many entities are understood not as objects, but as stable behaviors of underlying systems. Sound waves are not objects, they are organized vibrations of matter. Ocean waves are not objects, they are patterns sustained by water, gravity, and motion. Gluons fit this category. They are patterns in a quantum field, sustained by symmetry and interaction. Lattice QCD makes this interpretation concrete. When physicists simulate the strong interaction on supercomputers, they do not insert gluons by hand as particles. They define the symmetry and the interaction rules. Gluonic behavior emerges automatically. Confinement, self-interaction, mass generation, and hadronization all arise from the same underlying structure. The success of these simulations is not limited to qualitative agreement. Quantitative predictions match experimental results with remarkable accuracy. Proton masses, jet structures, energy distributions, and thermodynamic properties of quark-gluon plasma all emerge from the same framework. Removing gluons from the description breaks the agreement instantly. This is why gluons are sometimes described as bookkeeping devices for symmetry rather than material entities. They track how color charge must change to preserve the rules of the theory. They encode how fields respond to one another. They are not optional, and they are not arbitrary. The deeper implication is that matter itself may be secondary to interaction. Protons are heavy not because they contain heavy constituents, but because they are regions where interaction energy is tightly confined. Forces are not external influences acting on matter. They are integral to how matter exists at all. This view aligns with a broader shift in fundamental physics. Over the last century, the focus has moved steadily away from substance and toward structure. Space and time are no longer passive backgrounds. They respond to energy and momentum. Fields are no longer invisible scaffolds. They are active participants. Particles are no longer indivisible points. They are excitations whose properties depend on context. Gluons sit at the center of this shift. They illustrate how deeply interaction shapes reality. Without gluons, quarks would not bind. Without binding, protons would not exist. Without protons, atoms, stars, and planets would not form. The visible universe depends on a phenomenon that never appears directly. Observations across vastly different scales are consistent with this picture. High-energy experiments at accelerators confirm the predictions of QCD in exquisite detail. Astrophysical observations of stellar structure and nucleosynthesis depend on the masses and stability of hadrons, which arise from gluon dynamics. Even cosmological models of the early universe rely on the transition from quark-gluon plasma to confined matter. Space-based observatories such as NASA, ESA, and the James Webb Space Telescope explore epochs long after confinement occurred. Yet their observations would be impossible to interpret correctly without understanding how matter acquired mass and stability in the first place. Gluons, though never seen, shape every photon these telescopes detect. The history of this understanding reflects a recurring theme in science. Nature often reveals itself not through direct observation, but through constraint. We learn what is allowed by seeing what never happens. Free gluons never appear. Fractional charges never appear. Isolated color charge never appears. These absences are not gaps in knowledge. They are signals of deep structure. Carl Sagan often reminded audiences that the universe is under no obligation to be simple in the ways we expect. He emphasized that explanation comes from following evidence, even when it leads away from familiar pictures. The gluon story exemplifies this lesson. The evidence points consistently toward structure over substance. This does not mean gluons are imaginary. On the contrary, their effects are among the most precisely measured in physics. It means their reality is relational. A gluon is defined by what it does, not by where it can be placed. Seen this way, gluons are less like particles traveling through space and more like rules being enforced. They ensure that color charge is conserved locally. They ensure that energy remains confined. They ensure that the strong interaction behaves consistently across scales. This perspective also clarifies why future theories must respect QCD so closely. Any deeper framework that seeks to unify forces or explain their origin must reproduce gluon behavior exactly. Even small deviations would lead to observable violations of confinement or mass generation. The margin for error is effectively zero. In this sense, gluons act as guardians of structure. They maintain the integrity of matter without ever presenting themselves for inspection. Their presence is felt everywhere and seen nowhere. As this series closes, the picture that emerges is coherent and complete. Gluons are real, indispensable, and experimentally unavoidable. They bind quarks, generate mass, shape nuclear matter, and govern the earliest moments of the universe. Yet, they never exist alone, never appear as isolated objects, and never leave direct tracks in detectors. That combination is not a flaw. It is a clue. It suggests that at the deepest level we can currently probe, reality is organized not around things, but around patterns of interaction enforced by symmetry. Gluons are among the clearest expressions of that idea. And with that understanding in place, the story of gluons comes to rest, not as a mystery unresolved, but as a lesson learned about how nature chooses to build a universe. If you are listening as this final thought settles, may the steady order beneath the complexity offer a sense of calm. The same rules that bind quarks into protons hold the stars together and allow the night sky to remain stable above us. Wherever you are, and however this journey has accompanied you, may the rest that follows be deep and untroubled. Good night.